Functions and inverses. When working with functions, this is now a summary of all of the functions that you do for grade 11 and matric, and what you need to know about the function. So I'm just going to talk you through this summary. I have also uploaded a picture of this. So you can just download the picture and print that for yourself, or just keep the printer on your computer, whether you study from your computer or from paper. Right, so we have the linear function, the quadratic function, the hyperbolic function, the exponential function, the log function, and then the cubic function. These are the functions, these are the basic equations or regular formula that you use. Before going through what's happening here, I just want you to understand something about transformations and reflections of graphs. It's very important to know, and if you understand that, it helps you a lot in understanding the big concept of graphs. Every graph has a certain form. So a straight line, if I use this type of formula, I get a straight line. Now the most basic straight line without having a m or a c value, really, y is equal to x, looks like this. Y equals to x squared looks like this. Y equals to 1 over x will look like this exactly there. Y is equal to a to the power of x without the other values if they are now 0. Y is equal to log x looks like this, and y is equal to x cubed looks like this, going through the origin there. Alright, so these are the basic functions, how they look like. Then I can transform the graphs, I can shape them differently, I can turn them around, I can flip them vertically, I can flip them or reflect them horizontally, I can reflect them over y is equal to x, I can move them up and down, I can move them sideways. And if you understand how these transformations and reflections are done, and you know how the basic graph looks like, that just gives you a very big global advantage on how graphs work. Right, so moving a graph up and down and sideways, this C value, the Q value, the Q, we don't do a Q value in log, so I'm not going to move this graph up and down. And this D value, the constant that I add to an equation, moves the graph up. If the constant is negative, if it moves the graph down. And then for a straight line, I really just move the straight line up and down. In that effect, I actually move it sideways also, because if I move a straight line that goes through this point, if I move it up, you can actually see I moved it from this point to that point also. So with a straight line, I don't really move it sideways, I just move it up and down, because it's one straight line that goes to infinity. If I move it up and down, it actually moves. For these graphs, this one, that minus p value there, the minus p value moves the graph sideways. And you will see there's a minus in the equation. If I have a positive p, it moves the graph to the right. If I have a negative p, it moves the graph to the left. But if my p value is positive, I will actually have something like x minus 3, because in the equation there's a minus. So if I have x minus 3, then I actually have a positive p value, which moves the graph that way. You will remember it seems counterintuitive. If you have x minus 3, you tend to think it's a negative 3, but then it moves to the positive x side. And if you have x plus 3, that is actually x minus 3, which moves the graph to that direction, right? But the p value, the value that I put in brackets with x, so if I add a constant to the equation, it moves the graph up and down. If I add a constant to the equation in brackets with x, so there with the x, I don't do it here, and I don't have a format here to do that. That's a bit more intricate, but just understand, if I add or subtract a constant in brackets with x, it moves the graph sideways. And then to reflect the graph in the y-axis, in the x-axis, to reflect it in the x-axis, I make y 0. Because if I have on a graph, if I have the negative y's here and the positive y's there, if I make the positive y's negative y's, can you see? Then I reflect it in the x-axis. And then to reflect the graph in the y-axis, I change the x values, the positive x to negative x and the negative x to positive x, to reflect it in the y value, in the y-axis. And then to reflect the graph in the line y is equal to x, what I would do is I take the inverse, so I swap x and y, right, in the equation. So that is how I'm going to do that. And if you understand that about graphs, that really helps understanding how the domain and range will change, how the minimum or maximum will change, whether you must use a positive a or a negative a, things like that just sort of links with one another. If you understand how a graph is moved up and down, how it's moved sideways, and how it is reflected above certain around certain axes. Okay, so this is how the basic graphs look like. Alright, for the quadratic equation, you have two formats. The ax squared plus bx plus c standard format for the equation. And then also the turning point format, where you write a is in brackets x minus b squared plus q. And in this format, I have the P and the Q, and I get from this format to this format by doing completion of the square. And I get from the turning point format to standard format by just multiplying this equation out. Then I get the format ax squared plus bx plus c again. Now both of these equations has their uses, but for the most part, having it in the turning point format really helps us a lot. Okay, so let's quickly look at, in general, the domain and range. If you struggle to find the domain and range, you can literally just take this down and go and study it out of your head. For the straight line, my possible x values, because the straight line just goes continually over the spectrum, my possible x values, my domain will always be all real numbers, and my range will also be all real numbers. These values for all real numbers, doesn't matter how the line is turned or moved. This is always my domain and range for the straight line. For the parabola, my domain is always all possible values for x. My range is limited. The graph doesn't have y values. If it looks like this, the graph doesn't have y values down there. And if it's facing downwards, then the graph won't have y values up there. And then if it looks like this upwards, but I move it up, then the minimum value will, all of the y values will be above the minimum value, things like that. So depending on whether my graph looks up or down, is facing upwards or downwards, I can say if my a value is positive, that means the graph faces this way, then y will be bigger than all of the y will always be bigger than the point q. You know, PQ is your turning point. We're coming to that. But my y value at the turning point is q. So then I can just say y is bigger than q. If I have it in this format, if I have it in this format, I must just go and calculate what q is. But your y value at your turning point, y will then be bigger than that. That's your range. If the a value is smaller than 0, that means you've got a negative a value. That means the graph is upside down, like that sad face. So if you have a negative a value, then you have a your range is that y should be smaller than q. Also, your y value at your turning point and all of your y values will be smaller than that. Okay, so for the hyperbole has two asymptotes, right? There, between these two curves and there. Now I can move that sideways and up, but I know my horizontal asymptote is Q and my vertical asymptote is P. So the value of P is my vertical asymptote, and then if I look at, there will be an asymptote, say for instance there between the two, and if I look at all the possible x values, x can be anything on the spectrum except for the vertical asymptote, because that x value does not exist, right? So this is always how your domain will look for this graph, is x is an element of the real numbers, all of the possible values, except for x cannot be p. And the same with the horizontal asymptote, which is q. Y can be all of the possible values, but it cannot be whatever that value of q is, because that y value does not exist. All right, so that is always your domain and range, depending on your P and Q values. But if you have your P and Q values, which you can just read from your graph, then this is your domain and range. You literally just put the value of P and the value of Q in there. Always, this is always your domain and range for the hyperbole. And then for the exponential graph, my domain is always all of the possible values for x, because it moves across and there's no gaps. So all of the possible x values will be in my domain. My range, if the graph, if the a value is bigger than 0, that means I've got a positive a value. Now for positive a values, my graph will always be above the horizontal asymptote. Even if it's bigger than 1, it looks like this, and if it's fractions, positive fractions, it just goes up that side and down that side. But if the a value is bigger than 0, then all of my y values will be above the asymptote, so y will be bigger than q. If my a value is a negative, smaller than 0, then the line will go down, so the graph will be below the horizontal asymptote. So if my a value is negative, then my y values will all be smaller than the horizontal asymptote's value. So whatever your horizontal asymptote is, which is the value where y is q. So that is then your range for the exponential graph. For the log graph, most of the time, 90% of the time, the graph will be this side. If you do have a function log a and in brackets minus x, then the graph will lie on this side. Then just change the domain to x is smaller than 0. But if you have a normal log function, it will always lie to this side, which is the positive x value. So your domain is x is bigger than 0, and all of the y values are possible. And you will see how these two have something in common. I don't move the log up and down and sideways that much as I do the other functions. We just do the basics of this graph. But the exponential and the log functions are inverses of one another. So you will see this is a reflection. This graph is a reflection of this graph in the y is equal to x line. So this part goes there and this part goes there. And then can you see the domain and the range swapped? And here my x is bigger than 0, where my there will be a vertical asymptote, but the vertical asymptote will always be exactly there because I don't move the graph. Here I move the graph, so my vertical asymptote can move. That's why I have the vertical asymptote value there. For this graph, you're not expected to move it. So the vertical asymptote will always be at 0. All right. And for the cubic function, again, my domain and my range is all possible values of x and r. There are no restrictions or asymptotes or places where the graph does not continue. So for all possible values of x, and for all possible values of y, I have values with the cubic function. Okay, so that's the domain and the range of these functions. Then just talking about the mapping, all of them are functions. We've established that. That is why we are calling this chapter functions. You remember vertical line test whether a thing is function. Now all of these are functions. If I move a vertical line across, it only touches the graph once. But not all of them are one-to-one functions. So if I do the horizontal line test, this one succeeds, so it's a one-to-one function. This one has two cutting points some places, so this is a more-to-one function. This one is also a one-to-one function, a one-to-one function, a one-to-one function, and a more-to-one function. Alright, so this is the mapping, and then you know for more-to-one functions, which is these two, only the quadratic and the cubic functions are more-to-one functions. And for the more-to-one functions, if you do go find an inverse of that function, you must restrict the domain to make the inverse function still a function. For these ones you can just find, for the one-to-one functions, you can just find the inverse. For the more-to-one functions, you must restrict the domain so that you only use a one-to-one function. For the parabola, this part, the one half of the parabola will be a one-to-one function, and the other half of the parabola will be a one-to-one function. So you restrict the domain there. For this one, the first up will be a one-to-one function, then the down will be a one-to-one function, the middle part, and then that part is a one-to-one function again. So there's three separate one-to-one functions that you can go and restrict there. Alright, then just important things to know, a few important things to know about each function. For the formula to find the gradient in this, the m value, there's a formula which you are more than comfortable with, I hope. Important to remember for the quadratic function, the p and q values is my turning point. So it's useful to know that p and q is a turning point, and that I can find p by using this formula minus b over 2a. If I have this equation, I can use minus b over 2a, and that is the value of p. And then I can just substitute a point with p and the a value that I have already to just go and find q. So you can use this formula without actually completing the square. Just excuse me a second, I'm just going to close the door. Alright, so sorry. So I can use this formula without actually going and completing the square to go from this standard form to the turning point form. And then for the hyperbolic function, it's important to know you will have a horizontal and a vertical asymptote, and the equations of those two asymptotes is the horizontal asymptote, the equation of that asymptote is y is equal to whatever the value of q is, and the vertical asymptote, the equation of that line is x is equal to p. And then for the exponential function, you just have a horizontal asymptote, no vertical asymptote, and the equation of that line is y is equal to q, because see how it's handy to know the q value. What does that do? It moves the graph up and down, and can you see I move the graph up and down with a horizontal asymptote, and I move the graph sideways with a vertical asymptote, and that is why the p value, which moves the graph sideways, will be the center of the the vertical asymptote or the center of the graph that I use to move it sideways with. And then for the log function, I also have a vertical asymptote, which in the cases that we work will always be x is equal to 0, which is the y-axis, is my vertical asymptote. It can move sideways, so I can actually have if I think about moving sideways, if I put a bracket there, x minus p, then that p value will be the vertical asymptotes value, same as with all of the other graphs, but we don't do that in high school. But it's good to know that anyway, so understand that it works, the same thing works throughout for all of the functions. And then for the quadratic function, there's 2 turning points, and I can go find those turning points by finding the differential of the function. So the first differential of the function, and if I make that 0 and solve for x, I find the 2x values of my turning points, and then I can substitute that to find the y values, the 2x values. I substitute into the function and find the corresponding y values. But I can find my turning points by making the first differential of the function 0, because the differential is the gradient of the line, and the gradient is 0 exactly there at the 2 turning points. All right, then the x and the y intercepts, for most cases, to find the y-intercept you make x0, and to find the x-intercept you make y0, with some, but you can use that always for all functions, but there's some things I just like to point out. With the straight line, you can make x0, but if you make x0, this says y is equal to c. So your y-intercept, you can make x0, or you can just take the value of c. And for the x-intercept, you make y0. For the parabola, you make y0 or x0 for the intercepts. And I forgot to say now here that the line x is equal to p. You remember pq is my turning point, and p is the x value of the turning point. So the x value of the turning point, if I go and draw a line through the x-axis from the turning point, the line x is equal to that p value, is my axis of symmetry of the parabola. So they do sometimes ask, give the equation of the axis of symmetry. Whatever your p value is, if you don't have it, you can always use this to find the p value. So x is equal to whatever the x value at the turning point. X is equal to p, that's my axis of symmetry. And here, same thing for the intercepts, making the other one 0, same thing. With this one, there will be no y-intercept, because my y is, where x is 0, which is the y-axis, my y-axis is a asymptote, meaning it doesn't have any values there. It will never cut the asymptotes, and the asymptote is the axis. So it will never cut the y-axis, so you won't have a y-intercept. But you can find your x-intercept by making y0. And for the cubic function, you can find your y-intercept by making x0 and your x-intercept by making y0. But your y-intercept will also be that constant there, because if I make x0, all of these 3 terms fall away, because all of them become 0, and then my y-intercept is just the value of d. Okay, so that is the intercepts of all of the graphs and how you find them. And then another important question that you must be able to answer, that they constantly ask, is for what values of x does this graph increase or decrease? And if you struggle with answering that, this will also help you. If you go and study this out of your head, this is acceptable answers. I will discuss this with you quickly. But I didn't have, it's just too much to really go and write it down here. So if you struggle seeing that, you can really just learn this out of your head and give that as an answer. So if my m value is positive, then the graph is like this. Then the graph will increase for all values of x. So if they say state whether this graph increase or decrease and for what values of x. So those are the two things. Does it increase or decrease? And then for what values of x? That's the other thing. Now, if the graph looks like this, or the m value is positive, my gradient is positive, then for all values of x, the graph is increasing. If the m value is negative, so my graph looks like this, it's going backwards, it's actually decreasing then. So if your m value or your gradient is negative, or your graph faces backwards on the sketch, then for all values of x, the graph decreases. Right, so you can learn this if you don't understand that, but hopefully that makes sense. For this graph, if the graph is a smiley face, so if a is 0, if a is bigger than 0, a is positive, my graph looks like this, right? Then I will have a decrease for that first part and an increase for that second part. And the values of x, if I think about the values of x, I know my turning point happens at PQ. So my x value there at the turning point is P. So everything smaller than P will be a decrease, and everything bigger than P will be an increase. So if you have a positive A value, if you have a smiley face graph, so that is a positive number there, 3 or 20 or whatever, you have a positive A value, then you will decrease for all of the values smaller than P and increase for the values bigger than P. And then I just said vice versa. So if my A value is smaller than 0, then I will have a graph that look like that, and then I will increase for the values smaller than P and decrease for the values bigger than P, if that makes sense. Right, so that is how this will work. And then for the hyperbole, can you see that this is decreasing like this? So if my k value there is positive, the graph looks like this. So again, if my k value is positive, then the graph decrease for all values of x except where actually I haven't put that in here, but for all possible values of x. But now remember, x can't be the value of p. There nothing happens really. Or if my k value is a negative, then the graph will look like this. And then can you see it's increasing. So if my k value is negative, then the graph will increase for all values of x. So you just go and see whether the function looks like this, then you write decrease for all values of x, or decrease for x an element of r. If the graph looks like this, or the k value is negative, you can either look at the graph or look at the equation. If my k value is negative or the graph looks like this, then I write it's increasing for all values of x, or increase for x an element of r. Alright, so this is the increase and decrease of the hyperbolic function. And then for the exponential function, this is quite intricate, because there's 4 scenarios that can happen. This is the basic function where my a value is a positive number, looks like this. Right? If my a value is a positive fraction, so it's a half or a third, but that's between 0 and 1, then the graph looks like this. Alright? And then if I have negative a, then the graph reflects in the x-axis. If I make the y negative and I go and multiply it out on that side, then I have a negative a. It reflects in the x-axis. So if I have a negative a, it looks like this, and if I have a negative fraction a, then the graph looks like this. So there's 4 scenarios. Now, can you see the black one there increases, the red one decreases, and for this one, I now drew it the same, but this one increases and that one decreases. But you can just remember, for values bigger than 1, for a values, if you look at the a value, for values bigger than 1, or if a is a negative fraction, meaning it lies between 0 and negative 1, right? If your a value is a negative fraction, or it's a big number, positive number or negative fraction, then you're going to say it increases for all values of x, for x an element of R. And if the a value there is a positive fraction or a negative number, so the positive fraction and the negative number decreases. So if you have a negative number or a positive fraction, between 0 and 1 is positive fractions, then you can say the graph decreases for all values of x, or for x an element of R. Alright, so this is what's happening here. And then for this function, most of the time it will look like that, and then you can just say x increases for all values of x, it's increasing, right? But sometimes if I make my y value negative, so if I have a negative log x, which can present itself in quite a few ways, because negative log x, I'm talking about that in the log videos, but negative log ax can be negative logs with base a of x, or it can be log of 1 over x, or it can be log of 1 over a x. So there's quite a few things that can happen. But if I have the negative log x form, then I just made my y negative, so I reflected it in the x-axis, and then instead of increasing, it will decrease like that. So then you will say for all values of x bigger than 0, actually, because x is only bigger than 0, the graph will increase, or if it looks like this, it will decrease. But it can also then make a negative x there, and then it decreases or increase, depending on. So for this one, I suggest after you plot the graph, just really go and see if it goes up either like that or like that. But it goes up, then it increases, and if it goes down, then it decreases, or if it goes down like that, it decreases. So here you'll have to understand how increasing and decreasing work, and if it's on this side, then it increase or decrease for x bigger than 0, and if the graph is on this side, then it increase or decrease for x smaller than 0. So here you'll have to go and evaluate what's happening on the graph. And for this one, this is also quite complicated, because there's a bit that increase, a bit that decrease, and a bit that increase if the a value is positive. If the a value is negative, the graph looks like this, and then there's a decrease, increase, decrease. But basically, you will have, if you look at your 2 turning points and the x values at the 2 turning points, after you find the x values of the 2 turning points, you will either have an increase and an increase smaller than the first turning point and bigger than the second turning point, or you will have a decrease and a decrease smaller than the turning point and bigger than the other turning points x values. And then if for this one you have a decrease between these, so x lies between these two x values. And for this graph where a is negative, you have an increase between the two x values at the turning points. So this is a bit complicated, but it is a high level thinking answer. So I can give you this to go and study out of your head for this one. You'll have to really go and understand how this works. All right. So yes, that is the increase and decrease. And then sometimes they do ask minimum and maximum values. They will ask you, does the equation have a minimum or maximum sometimes? And then say, give the minimum or the maximum. Now for a straight line, there's no minimum and maximum. For hyperbole, there's no minimum and maximum. For a log function and a cubic function, there's no minimum and maximum. The only two functions that really has a minimum and a maximum is the parabola and the exponential graph. Now the minimum and maximum, whether it will have a minimum or maximum, depends yet again on the a value. So if the a value is positive, I'm just going to draw here the parabola. I know it's in the log. I'm just have some space here. So if the parabola's a value is positive, the graph looks like this, right? And if the a value is negative, the graph looks like that. So if it is a positive a value, the graph will have a minimum point, and that minimum point will be the y value at the turning point, which is q. If the graph is the a value is bigger than 0. If the graph has a maximum value, the graph will have a maximum point. If the a value is negative, the graph will have a maximum point, and that maximum point, the value of that maximum will be the y value at the turning point, which is the q value. Alright, so that is how you decide minimum maximum. For this case, you have a minimum with the minimum is q, and for this case, you have a maximum with the maximum also the value of q. Alright, and then lastly, quickly, the minimum and the maximum of the exponential function. Now you saw here, I said this is positive a values and this is positive fraction a values, right? Like a half and a third and a quarter and things like that. But bigger than 0 values will lie above the horizontal asymptote, and negative a values, whether it's a fraction, whether it's a negative value like -2 or a negative fraction, the graph will lie below the horizontal asymptote. So, yet again, if I have a positive a value, the graph will lie above my horizontal asymptote, and my horizontal asymptote will be the minimum, which is the value of q, right? And if I have a negative a value, the graph will lie below the asymptote, and then I will have a maximum value there, which is the value of the horizontal asymptote, which is q. Okay, so yes, so that is the maximum and minimum. The other functions don't have maximum and minimums. And I really hope that this summary helps you a lot. The thing is, it doesn't help you to watch the summary once and then you have it and then you understand it all. You really have to go and sit and study this. You really have to know all of this. You need to know, you need to be able to clear this space and go and write all of this on your own out of your head. If you can do this summary out of your head, then you know this stuff, and then this will actually really, really help you in the exams and with graphs, and you will see just really speeds up your understanding and your global understanding of how graphs work, and you'll be able to answer all sorts of questions, even if they change the question a little bit. If you are able to write all of this out of your head and you are able to explain to somebody else how a graph moves up and down, how it moves sideways, it really, really, really helps along your understanding of functions. So if there's one thing, and functions, in my opinion, is the most important chapter in high school maths. Really, this is what maths is all about in high school. So if there's one thing I want to really encourage you to go and sit and study, it's this table. Right. So really go and prepare yourself on this. Really go and learn this table out of your head. And then tackle the rest of the functions chapter with me.